be presenting my research, which is CFD investigation on thermal comfort and ventilation using 4 low-rise urban configurations in extreme climates. Okay, so I was able to have Dr. Hassam and Dr. John help me in finalizing my research. Okay, so these are the aims and the objectives of this study. Basically, one of the main aims is to identify the optimum urban configuration in achieving the most efficient natural ventilation behavior, and how arrangements or how building configurations can augment airflow throughout the community, and emphasizing its importance. So the CFD methodology, so the numerical investigation was carried out using CFD. The study uses 3D study Rand's equations, which utilizes the K-epsilon standard turbulence model. In terms of the pressure-velocity coupling, simple algorithm is applied. So you can see on the right-hand side are map images of the different locations. First, you will see Wasel, and then you'll see Dafsa, Cedar Villas, and the England cluster. All these locations are in Dubai or the UAE, and they have been chosen for their unique characteristics. These are the 3D models constructed from solid edge, and what I'm showing you right now are the buildings from each community for Wasel, for Dafsa, for Cedar Villas, and the England cluster. These are the meshed models. So because of the complex geometries modeled for each community, unstructured tetrahedral meshing was applied. These are the boundary conditions applied in ANSYS Fluent. And of course, to ensure that the CFD results are not dependent on the mesh, validation has to be carried out. So to validate the computational model, an independent grid test has been executed with the Wasel configuration over 12 grid solutions. Please note that the output perimeter used is taken from the surface of the outlet. And these are the graphs I've created to show you the outcome of the grid independent test, which shows the results for the outlet velocity, maximum velocity, and the outlet pressure. So you can see here that I have marked a point over there. So after that marked point, you can see that there are no rapid variations occurring after that point. So that means that this point can be deemed as a good mesh for the calculations and can be considered good with a less computational time. Okay, so the results. Note that in all the contours that I will be showcasing, the plane height is at 2 meters, which is the typical pedestrian level in determining thermal comfort. Okay, so first for the Wasel configuration, we can notice here in the images that high temperatures can be found within the configuration. You'll notice as well that around the narrow spaces, high temperatures are occurring as well as low velocities. Among the wider spaces, relatively wider spaces, you'll notice that there will be lower temperatures along with larger velocity values. So Wasel's configuration kind of does imply that large spacings may induce greater airflow movement. Next is the Dafsa configuration, the second configuration. So as you go deeper into the configuration, you can see that temperatures are rising, and this could be because that there aren't enough air velocity reaching those areas, so that would encourage hot spots, and it would avoid wind from carrying off enough heat from these areas. From the velocity streamline image, you can see here that airflow does go through the community, but some areas do not receive that airflow. And so since these areas do not receive much airflow, this also encourages hotspots in those areas, thus resulting in soaring temperatures. The next configuration we have are the Cedar Villas, which is a third configuration. We can observe here that as wind hits these villas, temperatures rise after contact. Most airflow, as you can see in the image in the velocity streamline, most airflow passes in between the villas, while some do not receive airflow. Notice that the pathways that are relatively more parallel to the wind direction result to have more airflow passing through, thus also having more or higher velocities in these areas. Now the fourth configuration is the Ingun cluster. So you can observe that the paths parallel to the wind direction over here, velocity is seen to increase, and so exhibiting the funnel effect occurring. So this is where wind speed would rise because of squeezing through narrow pathways. So you can see here that the funnel effect is appearing here. So paths exhibiting the funnel effect would reach around 7.84 meters per second, which is a lot higher than the inlet velocity, which is 6.67 meters per second. Now, because of the unique arrangement of the Ingun cluster, it has induced the funnel effect, which results in higher wind velocities occurring in the area. And so I also would like to mention that I had enough time to simulate a second set of results. This was to study the effect of decreased wind velocity using 3.34 meters per second. So basically in my first set of simulations, I used 6.67. In my second set, I only used half of that, half of the original inlet velocity. And so you can see the results on the right-hand side here. I know that the results don't seem so obvious, but I can assure you that temperature did rise in some spots or areas of the community. And you can also see that noticeably the DAFSA configuration has higher temperatures.
3-minute warning.
Okay. I'd also like to mention that I have created a temperature versus velocity graphs for the first simulation. So as we can see, all the graphs here are showing similar trends, where we can see that there is an inverse relationship between temperature and velocity. So that means as velocity increases, temperature decreases. So this information is for Wasel, DAFSA, and this one is for Cedar and the Ingun cluster. So you can see that they're all similar in trend. And then this table here, I would just like to mention is the velocity and temperature average values. What I'd just like to point out are the velocity values where Wasel and DAFSA are quite similar, where they only have a small minimal difference. But what's interesting here is the temperature difference. Although they have the same velocity, their temperature was still quite high of a gap, which is around 2.6 degrees Celsius difference, which might say that it's because of Wasel's configuration. It may have influenced its relatively low temperature, and it also may have to do with how it was designed to allow proper ventilation to encourage heat removal. So DAFSA, as you can see, has the highest temperature along with the lowest velocity, and Cedar Villas have the highest in velocity while also having the lowest in temperature. Okay, and I've also done this table where I have created this comfort temperature column, and you can see that I have calculated this based on a study by Ahrens, where it was said that if air velocities reach 1.5, 3, or 6 meters per second, the upper limit of the summer comfort range can extend as high as 33, 35, or 37 degrees Celsius, respectively, while maintaining a relative humidity of 40%. So I'll just show you a brief example for Wasel. The velocity is 2.72, and the interpolated and comfortable temperature would be 34.6. However, the actual temperature would reach 36.78, which means that it would exceed the comfort temperature. So I have done that for all the communities here. And so we can see that Cedar Villas actually reaches the most the closest to the acceptable temperature, because it could probably because of the linear arrangement and the open spaces between the buildings, which allow or encourage wind to smoothly flow throughout the community, thus avoiding heat accumulation and discomfort. So what I'd also like to say is that here in terms of thermal comfort, as I said, Cedar Villas were the most thermally comfortable out of the 4 communities. And if you would like as well, here's a summary table of the results for your perusal. If you would like to see, this is just a comparison between the first set of results, which use 6.67 meters per second and 3.34 meters per second. And that is all. Thank you for your time and thank you for listening.
Thank you very much. Perfect timing. And no, it's interesting to see the modeling work and scenario you've done for different building typologies. And I look forward to seeing how this then gets applied. I mean, especially with kind of retrofitting buildings and also kind of the post-pandemic recovery. So thank you very much for your excellent presentation. We're moving on to the last presentation of this session, which is